Okay, so I think we can start now. So hello everybody and welcome to this second invited talk of Netis. So it's a great pleasure for me to introduce you Akash Lal, who kindly accepted to give a talk to us in this conference. So Akash is one of the most the best experts in the area of program analysis, programming languages in general. So he worked especially on the verification and testing of concurrent and distributed systems. So he got his PhD from Wisconsin, University of Wisconsin at Madison, under the supervision of Professor Tom Rebs. And after that, he joined the Microsoft in India, in Bangalore, where he is now a senior researcher. So today he's going to talk about one of his works. Uh, so this is about the Coyote framework, which is used for the verification of distributed systems. And especially concurrent distributed and widely used in many applications at Microsoft and also at Amazon and so on. If I'm not wrong, I let him to explain this much better than me. So yeah, Akash did a lot of influential work, so we are happy to hear him and to learn from his experience today. So please, Akash, you have the floor. Thanks.
Uh, Thank you, Ahmed. Thanks for the introduction, and thank you to Netis, to Amin, and the organizers for giving me a chance to present here and to talk to all of you. Um, so I'm going to be talking about one of my projects that I've been working at Microsoft Research. This work spans multiple years. Um, and a lot of this work has been done by my collaborators, and I speak on their behalf. So this covers a journey of roughly 5 to 7 years on how this project has come up, what problems we've tried to address, and where it's getting used now. And I'll try to touch on both aspects of the project, the research aspects of the project, the research that went into it, as well as the engineering side of it, and the engagements that we've had with our users. So, as I go through this talk, feel free to interrupt. There are a couple of options. You can either send questions on the chat, and I can answer them asynchronously, or you can raise your hand, and I think I should be able to see your hand raised, and I can call you out for your question. Yeah, so feel free to interrupt. Let's make this interactive. The thing about having conferences online is that you miss these conversations, you miss engaging with people and talking, and that's where most of the learning happens. So let's have that. Let's keep that going. Okay, so this talk is naturally about concurrency. I won't spend much time on motivating this problem, but roughly concurrent programs are everywhere, right? I mean, it's fundamental. Concurrency is fundamental to computer science. Concurrency is what we use to build scalable systems. It's there everywhere, and more and more developers are getting exposed to writing concurrent programs. And the trouble is that they are hard to get right. If you programmed with concurrency, it's hard to test them. They become non-deterministic. You run them once, you get some output. You run them again, you get a different output. And whenever you hit a bug, it's not always possible to reproduce these bugs. So these are all challenges that come with the domain of writing concurrent systems. So let me try to explain that a little bit, right? So let's try to imagine ourselves as a software developer who has just joined a new company, and we've been given a task by our manager to write the code implementing a simple dictionary data structure. right? So think of this dictionary as a key value store, keys mapped to values. That is what we must do. So now, if you're programming in C sharp, the way I would start approaching this problem is that, well, I design my class, I design my interface. These are the APIs that I have to implement. I have to implement an add key, a contains key, a remove key, right? I write the code for this class, and I go back to my manager, and the first question would be that, why do you think your code is correct, right? So I have to make sure I test my code. So I will, what I would do is I'll write a test, and the test will look something like this. You instantiate your dictionary, you call some operations, you call some APIs on it, and then finally you make an assertion saying, the right thing happened, right? And I'm going to write a bunch of these tests, and now I can go back to my manager saying, these tests are good, they're exhaustive, and I think my code is correct, right? This is fine. This is well understood. Everybody does this. Trouble happens when you start having concurrency. So let's imagine the same situation again. So the next task we've been given, um, in order to get promoted in our software engineering job, now we must write a concurrent dictionary, right? So it's the same problem as before. It's still a key value map, uh, but it must support concurrency. That is, it should be able to allow multiple threads to access the data structure at the same time, right? And so, these are the kind of things that you have to do in order to improve the scalability of your system, improve the throughput by letting multiple, a lot of work happen at the same time. So part of this work is the same, that you define your APIs, your methods, and you write the code for them, right? Writing this code is also, not as straightforward as before. I think even as soon as you even hit a dictionary, you have to go consult your textbooks, read up your algorithms. Some of these algorithms are non-trivial, right? So now your manager has even, more doubts whether you got your code right. Now it's not a simple activity as just, you can read your code and understand whether it's correct or not. So, but now how are we going to test this? How are we going to test the fact that the dictionary is actually correct? Because it allows concurrency, right? So the same kind of unit test that I wrote before, if I write it now, this is not good enough, because this unit test here is not exercising concurrency, right? So if there are any bugs related to the design of concurrency in my algorithm, I will not be able to catch them, right? So things like, think of things like race conditions and so forth will not be caught by sequential tests. So naturally, you want to have some kind of concurrency in your test, right? This is what you would like to write. So this test here, what it's doing is now it's calling all these APIs concurrently, right? So you see this, this is C# syntax. So you see this task.run, which takes a lambda and just, runs the lambda in parallel. You wait for your tasks to finish, and now you assert something about correct behavior in your code. Unfortunately, people don't write this kind of tests. And the reason for that is actually twofold. It's because, when you write a program like this, in fact, your test is going to be flagged as a flaky test, because it's, when you run this test, sometimes it may pass, sometimes it may break, right? It may not be possible to reproduce the same error multiple times. And furthermore, you don't even know whether you're going to get concurrency. Whether you're going to get coverage in these kind of methods, in these kind of tests, because the execution of these tasks is not in your control as a programmer, as a person who's writing these tests. So so what do people do? I mean, surely, everybody writes concurrent programs, so they must be testing them. So what do they do? The common practices today is to resort to some kind of stress testing, right? So the situation is that instead of writing a test that looks like what I'm showing here on the slide, what you would instead see are tests that take a large workload, right? Lots and lots of APIs, thousands of times, and then, just stressed your implementation, making sure that nothing bad happens, right? There are a few problems with doing stress testing. First is that, the fact that you're, by exercising a large workload, the fact that you're going to get good coverage of concurrent behaviors in your code, that's just on hope. that's not directly something, so it's not a scientific argument that stress testing is going to give you good coverage. So that's one thing. The other thing is, even if your stress tests find a bug, so you hit a assertion failure, your test fails, it's very hard to reproduce that failure. And this situation actually is not rare. It happens many times that debugging the failure of a stress test is a very difficult problem. And in fact, the genesis of this project was in a similar situation where we were working with a product team. Well, I mean, the product team had designed a new storage, algorithm for distributed storage. They had stress tests going. So all their unit tests, integration tests were passing, but their stress test was failing. So they knew that they had a bug. And if you are, working in a team like Azure Storage, who is responsible for, storing your data, you do not want to ship with bugs in your code, right? So now, then they were not able to figure out how to address that bug for a while. It took them a long time to figure out what the actual problem was. But there's actually one other problem with writing stress tests is that as soon as you start exercising lots and lots of APIs, it actually becomes very hard to write a good assertion for correctness of your code. Right. So here I can, you can kind of still reason whether this assertion is valid or not, because, there's just a few tasks that you have to reason over. But if you have so many, if you're going to fire thousands of tasks, just writing good assertions becomes hard. So it's hard to, write good stress tests. All right. So what the research community has done is to try and address this problem and try and arrive at a situation where writing tests like this is how you do unit testing of your concurrency. This is what we want to enable. And the answer to that is this theme that I have termed here as controlled concurrency testing. So not everybody in the literature follows this term. Some people call it systematic testing. Um, some people call it model checking. So there are multiple names for it. But the idea is the following: that what you must be able to do is to deterministically execute your concurrent program in a fashion that you can then start enumerating the state space and covering multiple behaviors of your program. All right, so this is what I depict here as this state space kind of a diagram. So so let's try to understand what this diagram means. So imagine every circle here is like a state of your program, right? Your entire code, the state of your heap, the state of your stack, your program counter, everything, right? So this circle captures all details about the state of your program. Think of it as like a snapshot of your machine. So now, when you have a concurrent program, these concurrent programs are non-deterministic because you don't know which thread will get a chance to execute the next step, right? So now we must be prepared to explore all of them, right? And in controlled concurrency testing, what you must be able to do is to reliably pick the thread that you want to execute next, and you schedule that thread. For example, let's say there are three choices here, that there were three threads in the program. So three choices, A1, A2, A3. I should be able to pick and decide which one I want to run next. If I decide to pick A1, then I execute that thread for one step. That gets me to state S1. Use the same choices of these threads again and again to get a deterministic behavior. And then if I change my choices, I'll get coverage and I'll start covering newer and newer behaviors. Okay, so now it's a state space exploration problem that you have a large state space defined by your concurrent program. Some of these states are going to have bugs, and your job is to find those bugs. Okay, so now it's a state space exploration problem. So this is where Coyote comes in. It's built with this motivation of allowing controlled concurrency testing for C#. So it's built to understand the C# concurrency, things like tasks, C# tasks, and C# also has these other things called async and await for asynchronous programming and so forth. So Coyote understands C# concurrency in a fashion that it can do this. It can implement this controlled concurrency testing for C#. And the goal is to allow people to do this kind of testing, like what I showed you for concurrent dictionaries. So people should be able to write these unit tests. And then instead of just running these unit tests naively, you run them through Coyote. You give them to Coyote, and Coyote will do the state space exploration for you. Right. So Coyote is a combination of a couple of things. It helps you write these unit tests. It also actually helps you write specifications, and it does state space exploration. So it has algorithms inside it that do this exploration. And I will actually talk about one such algorithm in this talk. So Coyote is completely open source. You visit the website, use it, check it out. You'll find more content there. So so the journey for Coyote has been that, in fact, it's found a home in some sense in Azure. And it is used, the most common usage is actually not for things like dictionaries. Usage is for distributed services that are today running in the Azure infrastructure. The reason for that is that, I mean, a lot of people today, when you're building any software service for the cloud, you're basically building a distributed system, and these distributed systems have a lot of the same concurrency problems. So that's where their Coyote is used. It's used for testing all kinds of distributed systems issues. It's used for unit testing as well as testing end-to-end scenarios of services. These graphs here are a kind of like a rough account of the usage that we see in Coyote today. So basically what we did is every time anyone runs Coyote, we collect a little bit of telemetry from that use to record how long Coyote was run for, how many bugs did it find, and so forth. So this is just a snapshot of that, showing that about 11 million seconds of testing is performed per month using Coyote, and you find 1,500 bugs or so. Okay, so the example I showed you was a concurrent dictionary, and then here I made a jump saying people use it for distributed systems. So what's the connection between the two, right? And it turns out that is a very simple connection, that distributed systems are just concurrent systems if you engineer them properly. So let me just give a quick example of that. So this is a snapshot of let's say a typical a distributed system. What it will so it consists of multiple microservices that are communicating with each other. And this diagram shows that there are clients that can interact with these microservices, and there is backend storage, and there are queues for asynchronous programming, and there is a database like a Cosmos DB that you attach to where you store your state and so forth, right? So imagine this as a picture of a typical distributed system, right? Lots of different networked services. Well, I mean, what we do is just think of them as just concurrent systems. So, and the way you do it is that the same way you do mocking when you write unit tests for any kind of an application. So you start by mocking out your distributed components. So you write a mock of your storage queue, you write a mock of your database. And these mocks you attach to the same piece of code that you have for running your services, and then you just launch your services concurrently, and and that's it. So your concurrent program then in that case is going to simulate executions of the original distributed system. So these are the kind of tricks we follow. These are standard engineering practices, and people make sure to follow these practices so that they can write good tests for exercising their distributed systems, and in a way that they can then give to Coyote for exploration. Right. So just building on that example a little bit, this is what a test will look like for the same, for the kind of service that I showed on the previous slide. right? This is pretty much what the Coyote test will look like. This is just a normal looking C# method. What it does is that it starts by instantiating your mocks, right? So, it starts by instantiating a mock database, a mock storage queue. And then these mocks are passed to my services, right? So let's say, my distributed systems consists of a control service and a data service. I instantiate them and I pass them pointers to these mocks so that instead of communicating with the actual database, they're going to communicate with the mock database, right? And because of the fact that both these services have the same mock objects, they are going to communicate with the same database, right? So you do these instantiations, you start your services concurrently. So you say task.run, execute my control service, task.run, execute my data service. These are going to run in parallel. And let's say after that you execute some client workload, which is I'm not showing here on this slide, but imagine you start your services, you exercise some workload, and then you finally assert that everything is okay in your test. So this is how people are writing their tests today. And then once you write tests like this, there is concurrency naturally. There is non-determinism. Um, and you take this test and you give it to Coyote, and it's up to Coyote to perform exploration. So um, I'm not going to go into too many details. There are papers that you can take a look at. So we had a paper last year in SOCC, which stands for Symposium of Cloud Computing, where we describe our end-to-end experience in working with a system like Azure Batch. So Azure Batch is one of the more popular Azure services, and we worked with that team to write components that were thoroughly tested with Coyote. And we report the results, we report the experience, with the challenges, and we also report the impact we had by leveraging Coyote to do testing of these kind of services. There were components that were developed that when put in production just simply worked without bugs. This is something new to see, systems being flighted free of bugs. And it also, importantly, it wasn't, using Coyote wasn't something that slowed down the engineering process. In fact, it sped it up. So as people got more confidence in the tests they were writing, they were able to add in new features much faster than they were able to do before. And so they appreciated that fact that any kind of technology that's helping them get to market faster is technology that people and developers appreciate. All right. Any questions so far? The next part of the talk is going to be more about the exploration algorithms themselves. What is the secret sauce inside Coyote that makes it work? Okay, I'll continue. So the part I'm going to describe here is actually one of the algorithms. So the strategy that we follow in Coyote is that Coyote doesn't employ just one single algorithm. And we don't expect one algorithm to be the best exploration strategy ever. Instead, Coyote implements multiple exploration algorithms. And in fact, what we do is, we wait and we look at all, everyone in the research community writing papers. And whenever we find an interesting algorithm, we just take it and we implement it in Coyote. And so we have a suite of different exploration strategies. And what we do is we just run a portfolio of them. We run a selection of these strategies anytime somebody wants to do exploration. And the reason for that is that we do not want developers to think about which exploration strategy is going to work better for their code. We don't want people to make that connection. And so instead, we just run multiple exploration strategies in parallel. So what I'm going to do here, I'm going to describe one of the exploration strategies. This was described in a paper published at Uppsala a couple of years ago. Okay, so let's step back and let's look at this problem of controlled concurrency testing. So like I said, some people call it model checking, right? And so there are two major themes, two major kinds of techniques that people use in this space. These are the two boxes that I'm showing here on this slide. One is stateful techniques, and the other is stateless techniques. So let me kind of explain what I mean by stateful and stateless. So stateful techniques, what they do is that when they do exploration, they insist on capturing the snapshot of the state of the program, right? So in my state space diagram, the circles I showed, the stateful algorithms insist on taking a snapshot of the state so that they can answer this question: have I seen this state before? Right? So now, if you have the ability of doing that, knowing if you have visited a particular state before, you can do things like DFS, depth first search, right? Your classical graph algorithms, you can start doing search like that. And these search are enumerative and they will cover the entire graph given enough time. Okay, so instances of these stateful techniques are tools like Spin, and there are other things like Zing. Um, the challenge with stateful algorithms is that insisting on the ability of taking a snapshot of the program means that it's very hard to run these techniques on actual code, actual implementations. If you have C# code, right, taking the snapshot of a running C# program is an engineering problem in itself. So what you will find is that these stateful techniques are actually rather applied more on models of programs, right? Not actual implementations themselves, but rather models of those implementations. So, Spin, for example, supports its own programming language. And in order to use Spin, you have to write a program in Spin's language, right? Um, so that's where stateful techniques lie. So, for a setting like Coyote, stateful, do not implement stateful techniques because, we can't solve this problem of taking snapshot of a running C# program. So that's a challenge. And so stateless techniques address that challenge, and they provide a much better starting point for us to implement in Coyote. So what do these stateless techniques do? So they, in fact, know nothing about the state of a program. Instead, what they do is they just keep a track of the sequence of actions that you have executed before, and they use those sequence of actions as a proxy for the particular state the program is in, right? Um, so there are several examples of it. Actually, stateless techniques you can even classify into being enumerative techniques that will, that's where you have things like partial order reduction and so forth for covering the entire state space of a program. You also have randomized techniques. In fact, the ones I'm listing here are all randomized techniques. So they give randomized or probabilistic guarantees of finding bugs or of covering your state space. Um, and there are several such techniques, and like I said, we implement many of these inside Coyote. All right. The challenge with these techniques still is that they're all designed on certain kinds of heuristics. And the way these heuristics, so I mean, in general, covering the state space of a realistic implementation is difficult. I mean, the state spaces are too big, and you probably will not be able to cover all of it, right? But you still want to find your bugs, and you want to find your bugs as soon as possible. So the way these techniques are designed is that they take inspiration from bugs that we have seen previously in concurrent systems, right? You take inspiration from those bugs, and then you design these techniques in a manner that will find those bugs quickly, right? So, for example, one of the popular heuristics in this domain is context bounding. So, and what it says is that you can often find your bugs by exploring just a few context switches, right? It's okay, not to have too many context switches between threads. Just a few context switches should be able to find your bugs. These heuristics are good. These heuristics are very useful, but they are what they are. They are heuristics. And they take inspiration from patterns of bugs that we have seen previously, right? They do not answer a question about unknown patterns or unknown bugs, bugs that you've not seen previously. In fact, you will not even know whether you're missing those kinds of bugs at all, right? So that is the challenge with these techniques. This is a challenge that we identified, and we thought that this is a great place to replace human reasoning with machine learning, right? Instead of humans making observations of patterns of bugs, we let algorithms figure out these observations by themselves. So that's where reinforcement learning comes in. So we have an algorithm, a search algorithm based on reinforcement learning. And in fact, it turns out to be a good match, right? So if you look at early literature on AI and reinforcement learning, it's all about state space exploration, right? So I think it's a great match for the kind of exploration that state space exploration that we have to do in program verification. So we implemented a classical algorithm called Q-learning. The reason we picked that algorithm was the simplest one we found, and that's what we started with, and it kind of worked well. Um, what the algorithm does is that we set out an objective for the algorithm to maximize coverage. And the algorithm must learn ways of doing the exploration in a way that maximizes coverage. So I'll talk a little bit more about that. And the good thing is that we do not tell it anything. The algorithm does not know that it is exploring, the state space of a concurrent program. It doesn't understand concurrency or anything like that, and it has to learn those kind of patterns by itself. Right, and also, as we go through this, I'll also explain some results, some evaluation that we did on the performance of this algorithm. Okay, so let's look at reinforcement learning, right? Before we get into state space exploration. So the setting of reinforcement learning, you basically have is a game between two parties. One is called an agent, and one is called an environment. And the game is for the agent to explore the state space of the environment. Okay, and so what the agent can do is that the agent picks an action and gives it to the environment. The environment executes that action, and the agent gets to observe the change in state of the environment, and it gets a reward, right? For the new state the environment is in. Now, uh, so so the goal of the agent is to learn an optimal policy. It has to learn a policy. How should I select these actions in a way that maximizes expected reward? Okay, so that's reinforcement learning. Oh, sorry. So one other point here, right? So like I said, so these algorithms, in fact, I mean, the good thing about these machine learning algorithms is that almost all of them are built to handle noise. In this particular case, the agent is not expected to have a complete observation of the state of the program, of the state of the environment. Instead, it's okay that even if it makes partial observations, what is called a partial state here, it only gets to see some part of the state of the environment. It doesn't have to see the entire state of the environment. Okay, so when we map it to concurrency testing, the mapping is kind of straightforward. The environment is the program, right? So we're interested in exploring the state space of the program, right? The agent is our scheduler, right? It's Coyote. The Coyote is the agent. The scheduler is the component that is responsible for selecting, which action to explore next, which thread to schedule next. The program executes that thread for one step and gets, tells and gives a reward back. Okay. And now this is, so like I said, we're not in a position where we can observe the entire state of the program, but that's okay. You don't have to observe the entire state of the program. We only have to observe some part of it, right? And in fact, we can phrase it as an abstraction. So what the scheduler gets to see is just an abstraction of the actual state of the program, right? And now you can play around with these abstractions. Okay, and what the agent is going to do. So this is, so our scheduler is going to implement the Q learning algorithm. And so what the Q learning algorithm does is that it learns these weights that are called Q values, right? So, these things, there is a Q value associated to every state and action pair. And the way to read these weights is the following. So when the agent is in a state S, meaning that when the agent thinks that the environment is in state S, and it has three possible choices of actions to take, A1, A2, A3, and then the way the agent selects the next action is based on these weights. So these weights are real numbers. It looks at these weights and probabilistically selects the next action in proportion to what these weights are. Okay. So it does something like this. It takes a weighted average over these Q values and samples that distribution to pick the next action. Okay, so that is what defines our exploration strategy. And over time, what is the algorithm is going to do is that is going to refine, it's going to learn these Q values in a way that maximizes its reward, right? That's what the algorithm is designed for. It's designed to maximize the reward. All right, so that's where the next our next trick comes in. So what is this reward going to be? So remember, our objective originally is to explore the state space of a program, right? So so what the way we do it is that we map that to a problem of maximizing the coverage of a program. And the way we maximize coverage is by giving a constant negative reward. So this reward here is always -1, right? Now, the algorithm, the scheduler algorithm, whenever it sees a negative reward, whenever it visits a state, it gets a negative reward, and that disincentivizes the algorithm to visit the same state again, right? Therefore, it must find ways in which to pick newer and newer states, and that forces it to maximize coverage. Okay, so let's see how this whole thing, oops, sorry, one second. So there's the update rules. Let me not get into that. This is just standard Q learning. So let me get into an example and see how this all comes together. So imagine I have a program and the program defines a state space that looks like the following tree. So initially, all Q values are 0, right? So that means there is no preference. So when you're in S0, there is no preference to pick between A1, A2, and A3. Each of them can be picked with an equal probability of 1/3. Okay, so now when I'm in S0, I'll pick one of these three things. Sorry. And let's say I pick A1, right? So I pick probabilistically. So let's say I picked A1 and I get into state S1. My Q values in state S1 are still 0. So then again, the next action can be selected probabilistically with equal probability 1/3. Let's say I picked S4. And at that point, now my execution stops. There are no enabled actions in S4. Basically, the test execution is done. At that point, the algorithm is going to revise its Q values according to the rewards that were given. And because these rewards were negative, these Q values are going to adjust so that the probability of picking these same actions reduces, right? So the probability of picking A1 reduces to 0.27, probability of picking A4 reduces also to 0.27. And now the next time around, I'm going to start my exploration starting from S0. Now it's less likely I'm going to explore the same execution that I saw before. Okay, so this is how the algorithm learns. It learns to stay away from the executions that it has seen before. But it's also important that this algorithm be probabilistic. And the reason for that is that we only are seeing, we're only making a partial observations of the state, right? We actually do not see the entire state of the program, right? So in some cases, it is actually important to revisit the same state again, because concretely it might be a different state, right? So that's why it's important that the algorithm stays probabilistic and we do not deterministically avoid the states that you have seen before, because then your exploration will suffer. Okay, so let's see how this whole thing works on taking an example, slightly more realistic examples. This is still made up, but hopefully, it shows it gets the point across. Okay, so what does this program do? So this program has let's say six threads, threads or workers or machines. And it's basically implementing a calculator kind of a program. So there is this. So let's call each of these boxes as machines, right? All of these machines are running in parallel with each other. So there's a calculator machine, and what that calculator is doing is that it's maintaining a counter value, an integer value, right? And all of these other machines, they are continuously sending operations to the calculator to perform, right? So the add machine is continuously saying add one, add one, add one, add one. Or their multiply is saying multiply the counter value by 2. There is a reset that says reset the counter to 0. There's a divide that says divide the counter by 2. And subtract, which says subtract 1 from the counter value. Okay. And furthermore, what we do is that this calculator is actually, let's say the counter is pinned to be between minus 5,000 and 5,000, right? Just to make it bounded. So you take a program like this, right? So now let's say our objective is to maximize the state space coverage in the number of counter values that I see, right? So imagine this is a concurrent program, right? It's just a concurrent program. And my objective is to cover all different behaviors of this, particularly all different counter values that are possible to exist in this program. Okay. So now here's a comparison that compares the coverage that Q-learning can provide versus the coverage that some of these previous techniques, previous exploration techniques can provide. So in these graphs, the x-axis is the number of times the program was re-executed, the amount of exploration that the algorithm was allowed to perform. And the y-axis is counting the number of unique counter values that we have seen so far in the exploration so far, right? So these graphs are naturally, monotonically increasing. So, random and PCT, think of them as previous techniques, they give you this kind of a coverage. And what you see with Q learning is that it is able to give you almost the entire coverage, right? So you note that only 10,000 counter values are possible, and you see QL actually almost hitting 10,000, much, much faster than what these previous techniques could do. And the reason it's able to do it much faster is because it's able to learn. So these previous techniques are actually agnostic to the semantics of the program. They know nothing about, counters or anything like that, right? But once you tell Q learning that the objective is to maximize the number of counters you've seen, it's able to learn much faster and it's able to do exploration much better than previous techniques. So this goes to show that once you start making observations of the state of the program, you can do your exploration much better than otherwise. Right, and just to give you a little bit more evidence of the learning that the algorithm is able to do, I've shown show some more graphs here. So in these graphs, the x-axis is again the number of the number of times you've executed the program, the number of times you've iterated through runs of the program, and this time the y-axis is the number of actions you picked. So the number of add operations you picked, the number of subtract operations you picked. So what you'll see is basically, in random exploration, you pick the next action randomly, uniformly at random. So there's no actually, the algorithm does not distinguish at all between doing a reset, subtract, divide, add, multiply. And same with PCT, it has some different kind of distributions, but it does not distinguish between these multiple operations. But what you see Q learning do is that it learns very quickly that reset is actually not a useful operation. Because every time you do a reset, you go back to 0, right? The counter goes back to 0, and 0 is a state that you've seen before. In fact, it's a state that you've seen many times before, right? So it learns very quickly that reset is not worthwhile, and it learns not to do resets. And also, in fact, it learns that multiplication is pretty good, right? At least initially, multiplication is great to get new counter values, and then it kind of converges. Add and subtract are symmetric, and it kind of knows. I mean, they stay with the same uniform probability, right? So these are kind of evidence of learning that the algorithm is able to do based on the semantics of the program that it sees. Okay. There is another example, which is slightly more realistic, but let me skip it in the interest of time. I have 10 more minutes, so let me just continue on with the talk and skip this part. Okay. So this is finally like a recap of the algorithm. The way it works is that inside Coyote, Coyote implements a scheduler. Then the scheduler is implemented as this queue learning algorithm, an algorithm that is learning these weights, these queue weights, right? Um, the penalty is, the reward is fixed to a constant negative penalty. There are some variations of it that we cover in the paper, but think of for now, just think of it as a constant negative penalty. And what is interesting here is that so there is an abstraction that we can play around with, right? So as we're executing a program, we get to make choices on what part of the state are we going to see? What part of the state, what abstractions are we going to work with? Now, these abstractions can be user defined. So a user, the programmer who is interested in testing their program, they can get to define these abstractions by themselves. But what we do is we also have a default abstraction. And this default abstraction captures some aspects of the concurrent program that we are able to see just by observing the state of the runtime of the program, right? So, this will be things like the number of threads, the locks they hold, the state of the network, and so forth. Things that are kind of agnostic to the actual program, but things we can make default observations about. Okay, so because of the fact that we are looking at the state of the program, but not completely, this kind of techniques are somewhere in the middle between stateful and stateless. Because you get to define how much of the state are you going to observe. Okay, so let me present some evaluation. So the way we did this evaluation is that every exploration we ran. Every experiment, it consists of n runs, right? Actually, ignore this m. So we take an experiment is defined by doing exploration of the same program n times, and then we repeat this experiment multiple times because this exploration is probabilistic, right? So we run the same experiment multiple times and then take an average among all the runs. Okay, so these are the results that we got. So let me walk through this table. So each row is a different benchmark. Every benchmark is a concurrent program with one known concurrency bug. Each of them has exactly one bug, and we know what that bug is. The benchmarks cover a variety of different kinds of concurrent programs. We have, protocols. These are distributed protocols. We have multi-threaded programs. Some of them are like data structures, concurrent data structures. And we also have these are production Azure services. And these columns are different exploration strategies, right? So I've not explained what these exploration strategies are. So let's not worry too much about that. And this is QL. This is our Q learning algorithm. And these numbers are the number of times you were able to hit a bug in a run among 100 runs, right? So we did the experiment 100 times, and among them, how many times did we actually manage to hit the bug, right? So higher, the better. And what we find is that among all of these benchmarks, that Q-learning is the only one that is able to find all of the bugs consistently, right? And the other schedulers miss multiple bugs among these 16 benchmarks that we have here. And not just that, in some cases, for example, Q-learning is the only one. So COD, for example, Q-learning is the only one that is able to find the bug. The other schedulers are not able to find it. And in some cases, the performance of Q-learning is much better than the performance of the other algorithms. Okay. Yeah, so covered multiple of these things. So bug finding is only one measure of success. It's not the only measure. Sometimes bug finding can be a little bit flaky because either you hit the bug or you don't. Coverage is actually a slightly more robust metric. So we do measure the state space coverage of the program. And what we see is that most cases, not all cases, but in most cases, Q-learning is able to explore the state space much faster than some of the other techniques. Right? It's not always the case, but we did find some correlation between being able to maximize coverage and the bug finding abilities. Okay, so this work is by far not done. There are several aspects of the problem that still remain to be addressed. So for example, I brought up this notion of using a user-defined state abstraction. A user can define what kind of state abstraction they want to use for exploration. We did do some experiments and we report the results in the paper on using different kinds of abstractions. And in some cases, we were able to improve the performance of the algorithm by changing the abstraction. In some cases, we were not. And I think just the general direction of defining abstractions that work well for reinforcement learning, I think is a very interesting problem that has connections beyond just concurrency exploration, that I think has more connections to program verification. So that's it. So that's what the talk is about. I demonstrated to you motivation for the problem, that the software engineering community really needs solutions for testing their concurrent programs. And this also is not just interesting for developers and engineers. It's also interesting for us as researchers because there are several interesting problems that we can solve in this space. Coyote has been a tool that we have developed over a number of years. It's been targeted to C#. And I covered, in this talk, I covered a couple of different papers that I'm showing here. There are, like I said, many open challenges. I talked about state abstraction already is one open problem for reinforcement learning. Other ML algorithms, for example, right? We just pick Q-learning. Can we do other things, right? Can we do deep reinforcement learning? Can we do transfer learning? So, for example, let's say, can we have our testing algorithm train on a suite of benchmarks, figure out the bugs in those benchmarks, and learn strategies that are able to find similar kinds of bugs in newer versions of those programs? Can we do things like transfer learning, right? Which is, I think, very interesting problem that we've not looked at so far. Besides just the exploration, I mean, the concurrency comes in many forms. In studying different, those forms can be interesting in itself. So, for example, the concurrency in C++ would be very different. Concurrency in Rust, Go are different than what they are in C#. And it's not just languages, but there are abstractions and interfaces and APIs that have their own concurrency semantics. In the database worlds, these are called consistency levels or isolation levels. In hardware, they're called weak memory models. Each of these are concurrency problems, essentially, right? And there are lots of interesting problems we can study there. And can, as a community, we need to have, can we define some challenge problems here, right? Can we define, can we verify? Can we test some of the most common concurrent implementations that everybody uses, right? Can taking something like a garbage collector, like you have in Java or in .NET, can you take a concurrent garbage collector and you can verify it for correctness? I think these are super interesting challenge problems that we can address as a community over time. So with that, I'll stop. This is the website. You go here. You can go here to learn more about Coyote. Use it. Have fun with it. And I am okay to take questions.
Okay, thank you very much, Akash, for this great talk. The floor is open for questions. Please raise your hands if you have any questions. Okay, I see already a question by Srinidhi. Please go ahead.
Hello. Hi, Akash.
Hi.
I wanted to ask you about the work you did with Raft. So from the example that you pointed out, it was clear that you could test distributed systems that had some sense of shared memory. For example, you had a shared database or a shared queue among the different services. So when you test Raft, you don't have any shared memory. It's just message passing. How do you model that, and how do you test that with Coyote?
Right. Yeah. Yeah. Good question. So, I mean, basically, what you have to do is you have to mock the network, right? And the way you mock the network is, I mean, there are many different ways of doing it, but one way is to, let's say, so every machine, every Raft node, you run concurrently. And when a Raft node has to send a message to another Raft node, what you replace that, the send on the network, you replace that with an enqueue into the queue of the target node, right? So simple strategy, right? You can make it a little bit more complicated if you want to have networks that can reorder messages or network that can drop messages, right? So you just plug in your network API, right? You mock your network API, you plug it in, and now you have a concurrent program, and now you can do exploration on that. So in this case, the shared state is the state of the network.
Okay. Okay. Thank you.
Thanks.
All right, so there is a question on the chat by Mustafa Shakir. He's asking, could you please repeat what are the problems with stress testing?
So three challenges, right? That I pointed out with stress testing. One is the fact that it gives you good coverage. That is not an established fact. So it's not true always that by stress testing, you're going to get good coverage of concurrent behaviors in your program, right? In fact, I mean, several papers have shown that systematic testing applied or controlled concurrency testing applied to small tests gives you better coverage than what you can get with stress tests, right? So coverage is one problem.
Maybe I can also give a complementary question to this one. Is okay, if I take stress testing, how it compares with random testing in on what you call random testing. So one is you build you consider your graph and then you do random. And is it different from stress testing? So you talked about random testing. So if there is a link on this too, maybe it explains something. I don't know. This is just a question, just to maybe to.
Sure.
But now
Yeah, no, that's a good question, right? So even with random exploration, controlled concurrency testing is much different than what you get in stress testing. The reason for that is when you're doing stress testing, you're running your concurrent program on your machine, on your hardware, right? And then it's up to the hardware and the OS to do scheduling in your program, right? And these systems are designed in a particular way, right? Systems are designed to give you performance, so they will do scheduling in a certain way that you get more coverage of one kind of behaviors and you do not get coverage of other kinds of behaviors at all. So what you need to do is, so for example, if you just take an example, let's say you have a program in which there are two instructions, one after the other, and you must interleave between those two instructions, right? Two assembly instructions side by side. The probability of interleaving right between them is very minimal when it comes to just running your program with stress testing and so forth, right? Because these systems are designed to just keep going, right? And when a thread is in context, you just keep running that thread. That's how these our systems are designed. But with random exploration, what's going to happen is that every time you hit a scheduling decision, you're going to pick one of the possible choices, right? So they're much more neutral to how they explore the program, and thus they give you better coverage.
Mhm. So can I say that stress testing is very dependent on the platform on which, or on the infrastructure on which the program is executed, and if this one can change uh, next year or in few years, so no guarantees are given in some sense about the previous testings.
That's right.
Whereas
Yeah.
this approach that you are applying, in some sense, they are more abstract or more agnostic to the platform on which these things are done. So they are
Right.
done for every possible, without any assumptions on the platforms or the infrastructure.
That's right. Yeah.
All right. So other questions? Please go ahead. So maybe in the meantime, I can ask about this question about this issue of abstraction for the abstract state,
Mhm.
because in some sense you move the problem to that place. So whether this problem is easier now to design the right abstractions in order to maximize the coverage is not clear, because all these coverage results will depend from the relevance of this abstraction. So, is there any relation that can be made between the type of abstractions that you do, or for instance, can this be defined in a in a way that it can be tuned somehow? See, like you have some kind of parameters, the number of whatever variables that you show, or maybe some static analysis of the program can determine what are the relevant variables or whatever to keep in the abstraction and so on. And then, so if the user requires some level of coverage, so you could guarantee it with that type of abstraction. You know which type of abstraction will guarantee at least this required coverage. Would that be possible?
Yeah, I think these are interesting questions. And that's actually the challenge. Yeah, that's the flip side of working with machine learning algorithms, right? There are advantages that I showed here, but the flip side is that they're hard to interpret, right? So I can illustrate that. So what we did in our experiments, so as you said, state abstraction is important. So if we use a naive state abstraction that just abstracts everything away, so everything is a single abstract state, then Q-learning will behave the same as random exploration, right?
Mm.
Basically, it will not be able to learn any bias. Everything will stay like a random exploration as it deteriorates to random, right? So state abstraction is definitely important. You can't also say that the concrete abstraction is the best one, because in the concrete abstraction, you have many, many states. So learning will be very slow. In fact, you will probably not learn anything, right? So both ends of the spectrum are in fact bad. You need to be somewhere in the middle for learning to kick in. What we did in our experiments is that we just said, okay, we're going to stay neutral to this as much as possible. So for any message passing program, our abstraction is just the state of the network, right? The set of pending messages on the network. And we just take a hash of all of that, and that we call is our abstraction of the program. And we find that it works well for these kind of programs that we tried. The next step would be actually to start interpreting some of these results and see what exactly is the learning that this algorithm is able to do, uh, and then use that insight to figure out what are the newer kinds of abstractions that I can use or cannot use, right? So
Mm.
for example, a machine learning answer to this would be to go to something like deep reinforcement learning. So now, so think of the problem like this, right? So your state of the program is this giant vector, right, of all the bits in the state of the program.
Mhm.
Today, we just take a few of these bits and we hash it, and we call that our abstract representation. But what
Mhm.
you can instead do is you can use machine learning itself to figure out which features of this big vector are important. So you can do an embedding, and then you can use that embedding to do learning. And I think
Mm.
that's very interesting, right? But
Right.
we have not gotten that far yet.
Yeah, absolutely. Yeah, great. So there is a question by Rupak. I don't know whether which Rupak is this one. Is it Rupak Majumdar? I don't know. So I cannot read, unfortunately, the whole message. Uh,
So
Rupak,
I can
you
see it.
can
I
read
can.
it. Ah, you can
Yeah.
see it. Go ahead. I had some problem. I cannot read the whole. Okay, go ahead.
Rupak is there. I see
Yeah,
him.
I can ask. I had some problem with the.
Ah, okay. Hello. Okay, go
Uh,
ahead, please.
yeah, so I guess yeah, you can read the question. My question was that you can have unboundedly many actions, right? And because you can have unboundedly many threads that are created, and how do you deal with that? And the other question is, what if you make the observable just the program location, right, as a natural extension to state just location coverage in sequential programs? Does Q-learning, do you have experiments that show how well it
Yeah.
works?
Yes. Yeah. So I can answer them, right? So the first question, unbounded threads. Well, I mean, because this is online exploration. We're taking the program and running it. We actually never hit the case where you have unbounded threads. But I guess the point there is that you have to be careful about how you do your state abstraction. If every thread is going to get a new, if you take the thread ID as part of your abstraction, your learning will suffer because you introduce you'll start distinguishing between things that you should not be distinguishing, and then your learning goes down, and then it doesn't work very well. So in fact, our state abstractions do not take a thread ID as part of the state representation, right? So even if you're
Okay, thanks.
spawning threads, killing threads, you still are learning something.
Thank you.
So the other question is, so for multi-threaded programs, our default abstraction was to take the program counter. And some cases it worked okay. In the safe stack example, it did not work. The Q-learning wasn't able to find the bug, or it found it very rarely. And then what we did is that we enhanced the state abstraction to also include an abstraction of the contents of the stack, the state of the stack. So we put that in also, and it worked well, right? And then we said, okay, this is good enough for the paper, and we left it at that. But yeah, knowing why exactly this happened, I think is interesting.
Okay. Thanks. So Gennaro has a question. Gennaro, please.
Yes, thanks for the talk, Akash. So I have one question. Do you learn with this machine learning technique from previously seen bugs?
Can you repeat your question? I maybe didn't
Do
catch
you
the whole of it.
learn from previously seen bugs in using this?
No.
Okay.
No, we don't know how to do it. We would like to do it. I think that's been one of the asks from product teams, that look, if you know how to find bugs in one version of my program, likely I know I'll hit the similar kinds of bugs in the next version, right? So how can you learn and improve your testing over time? We don't quite know. The way the algorithm we've set it up today, we are not able to transfer learning from one version to another. Yeah.
And another question, would this technique be useful to understand the probability of hitting a control flow point in a bounded program? So I would like to learn how the runs are distributed across the control flow point of the program.
Yeah, I mean, I think you can do it. Yes.
All right.
I think, yeah, you can use these Q weights and you can figure out these probabilities. Yeah.
Okay. I'll get in touch then. All right. I'm done with this.
Okay.
Thank
you very much. Other questions? Maybe if there are some other questions. Otherwise, I think we can thank Akash for the great talk and very interesting perspectives for this research work. Thank you very much again for your talk and for being with us. So, and right, anyway, so I guess if there are other questions, people could look at your papers and
Or
your,
send me email. Send me email.
or can send
no
you
worries.
an email. Thank you very much. Okay.
Thank you.
Thanks everybody, and see you. Bye. Bye-bye.
Bye.
Bye.